Hello everyone, good morning to all of you. So today we are going to discuss the enthalpies of the reaction. So this is actually one of the most important concept in thermochemistry. So in the earlier class we discussed about bomb calorimetry and water calorimetry and how to determine or how to calculate change in enthalpy and change in internal energy. Okay, now in this session we are going to discuss the enthalpies of the reaction. So what are enthalpies of reaction? And under the enthalpies of the reaction, what is enthalpy of combustion? What is enthalpy of formation? And what is enthalpy of solution? And what is enthalpy of neutralization? And what are enthalpy of phase transitions like enthalpy of fusion, enthalpy of vaporization, and enthalpy of sublimation, and enthalpy of transitions, and finally Hess's law of constant heat summation. So these are the concepts we are going to discuss in this session. Okay, let us restart. The first one, enthalpies of the reaction. What is enthalpy? Enthalpy is nothing but heat content. So during the reaction, the reactants are converting into products. So while the reactants are converting into products, what are the heat changes? Whether the reactants are absorbing the heat energy or the reactants are liberating the heat energy while they are converting into products, and that change of heat content we call it as what? Enthalpy of the reaction. So enthalpy of reaction is nothing but the change in enthalpy, enthalpies during the reaction is called what? Enthalpy of reaction. So simply we represent this as delta HR, and delta HR, that is change in enthalpy of reaction, is equal to, so difference between enthalpies of, sum of enthalpies of products, P stands for products, minus sum of enthalpies of reactants. Sum of enthalpies of products minus the sum of enthalpies of reactants, and that difference we call it as what? Enthalpy of reaction. It can be exothermic or endothermic. Exothermic means del H value was negative, and endothermic means del H value was positive. So under these enthalpies of reaction, we will discuss the first one, enthalpy of combustion. Combustion. You know what is the combustion? Burning in presence of air or oxygen. A burning of any substance we call generally as combustion. Enthalpy of combustion. So this generally we represent with the del H combustion comp or del HC. Del H comp or del HC. So this is a usual representation of enthalpy of combustion. And sometimes what happen, del H naught C or del H naught combustion also may give. Okay, so what is the difference between del HC and del H naught C? Del HC is what? Just enthalpy of combustion. Del H naught C is a standard enthalpy of combustion. So what is the difference? Standard enthalpy of combustion is nothing but combustion of a substance, combustion or burning of a substance or 1 mole of the substance in presence of excess of air or oxygen when that substance is at their standard physical state. Okay, standard physical state. Then that is called what? Standard enthalpy of combustion. Here I am writing the definition for the enthalpy of combustion. That is what? The change in enthalpy. The change in enthalpy when 1 mole of substance, completely burns, in presence of excess of air or oxygen. See here, compulsory the substance should be 1 mole. When 1 mole of the substance is completely burned And while burning of that 1 mole of the substance, whatever the heat changes takes place, that's we call it as what? Enthalpy of combustion. For example, here I am taking carbon. When carbon, see here how many moles of carbon I have taken? Coefficient is 1. So that means 1 mole. When 1 mole of carbon on combustion, heating in presence of oxygen, the carbon is converting into what? Carbon dioxide. Here how many moles are combustion? 1 mole. So whatever the heat changes, that is what del HC here is nothing but is equal to minus 393.5 kilojoule per mole. That means when 1 mole of carbon undergoing the combustion, total how much of energy it liberates? 393.5 kilojoules of heat energy it liberates. And see, this is the same thing we can write del H naught when the element, when the substance is in its standard physical state. What is the standard physical state of carbon? Graphite. So if you take that carbon is in graphite form, 1 mole of the graphite on undergoing the combustion, releasing the carbon dioxide. During this, whatever the change of heat energy, that is called standard enthalpy of combustion. This is the value of standard enthalpy of carbon. Similarly, if you take hydrogen, what is the standard physical state of hydrogen? Generally at room temperature, it is a gaseous state. H2, when 1 mole of hydrogen undergo combustion, it forms H2O. And it is also exothermic, so that is equal to minus 8 to 85.8 kilojoule per mole. So these all are examples. Or else methane, if you take, when 1 mole of the methane undergoing the combustion, it liberates nearly 890.4 kilojoules of energy. So these all are what? Enthalpies of combustion. Once again, the change in enthalpy when 1 mole of the substance completely burns in presence of excess of air or oxygen, we call it as what? Enthalpy of combustion. Next, move to the applications of this enthalpy of combustion. So what are the applications? See, if you see the applications, the first application of this enthalpy of combustion is calculation of enthalpy of formation of compounds. By using this enthalpy of combustion, we can calculate the enthalpy of formation of the compound. Here a new enthalpy. What is that? Enthalpy of formation. So first one already over, enthalpy of combustion. The second one is what? Enthalpy of formation. That we simply represent with the del HF. Okay, we will discuss what is this enthalpy of formation, everything we will discuss. So anyhow, this is the first application, calculation of enthalpy of formation of the compounds. And the second application is calorific value. Calorific value of the substance we can calculate. You know, even if you buy any food product, at the wrapper of that food product, there was a calorific values. How many proteins, how many fats, how many carbohydrates, everything is there. So that is what calorific value. Yes, how we calculate this calorific value? What is calorific value? It is nothing but the energy, at the total amount of heat energy liberates when 1 gram of the substance completely burns. When you take that 1 gram of that substance, if it completely burns, whatever the heat energy liberates, that energy we call it as what? Calorific value. So calorific value is nothing but the ratio between the total heat energy liberates divided by its molecular weight. Simply if you divide the total heat with its weight, then we'll get 1 gram. When 1 gram of the substance undergo the combustion, whatever the heat energy liberates, that is called calorific value. Remember that. Okay, generally the units for the calorific value. This heat energy, here we can express this heat energy in calories or else joules. Suppose if we express the heat energy in joules, then the molecular weight we express in kilograms. So the units of calorific value can be joule per kg or calories per gram. So usually we can express this calorific value in these two units, either joule per kg or calories per gram. Suppose generally we use this one. So in how you define this calorific value by using these units? The total heat content in calories liberated when 1 gram of the substance completely combustion, then that is called calorific value. So this is what these are the two main applications of enthalpy of combustion. So in the first application, new enthalpy, that is what? Enthalpy of formation. Let us discuss what is enthalpy of formation in detail. Enthalpy of formation. So what is enthalpy of formation? It's nothing but the change in enthalpy when 1 mole of the compound is forming from its constituent elements. Okay, just give you an example. I wanted to prepare carbon dioxide 1 mole. To prepare 1 mole of the compound, what are the elements of the carbon dioxide? To prepare the CO2, we need carbon and oxygen. So the elements is carbon and oxygen. Okay, so when these elements undergo the reaction and producing what? 1 mole of the compound. During the formation of 1 mole of the compound, from its constituent elements, whatever the heat changes takes place, that is called what? Enthalpy of formation. In the name itself it's there. Enthalpy of formation. The change in enthalpy during the formation of 1 mole of the compound from its constituent elements, okay, at STP is called what? Enthalpy of formation. Here, the change in enthalpy when 1 mole of compound is forming from its constituent elements. Okay, that is called what? Enthalpy of formation. See, you may get the doubt. See, this is what enthalpy of formation with respect to CO2. And here, when 1 mole of the carbon undergoing combustion, see, heating in the presence of oxygen, what we call enthalpy of combustion. So we can write one thing, enthalpy of combustion, del Hc, enthalpy of combustion of carbon is equal to, enthalpy of combustion of carbon is equal to enthalpy of formation of CO2. So the enthalpy of combustion of any element, not only carbon or carbon dioxide. Suppose here if you take hydrogen, H2O. Enthalpy of combustion of hydrogen is equal to enthalpy of formation of its compound. What is that? H2O. Okay, so likewise. So enthalpy of combustion of any element. So we can generalize, we can finalize this reaction as enthalpy of combustion of any element is always be equal to enthalpy of formation of its corresponding compound. Okay, and this formation enthalpy, it can be exothermic or endothermic. Okay, it can be exothermic or endothermic, whatever it may be. So it depends upon the nature of that compound. Okay, so this is about the enthalpies of formation. See how we can calculate formation enthalpies from combustion enthalpies. Let us see. I am taking 3 combustion reactions. What is that? The first combustion reaction, CH4, methane combustion. When methane on combustion, we get CO2 plus H2O, and where del H1. So the change in enthalpy of first reaction I am writing as del H1. So del H1 is equal to minus 890.4 kJ mole inverse. That's the first equation. The second equation, C plus C graphite. Graphite carbon on combustion, we are getting CO2. Okay, so here enthalpy of combustion del H2 is equal to minus 393.5 kilojoule per mole. Next, third equation I have taken, that is what? H2 combustion. H2 plus half O2 gives rise to H2O, and whose enthalpy of combustion is 285.8 kilojoule per mole. See, three combustion reactions they have given. Okay, now we wanted to determine formation enthalpy of methane. Formation enthalpy of the methane. What is the methane formation? See, methane general formula CH4. This is the compound we need. To form this methane, we need carbon and hydrogen. So C plus H2. How many moles of H2? 2 moles. H2 gives rise to CH4. This is the net reaction we need. During this formation of CH4, whatever the changes of enthalpy, del H value we want. Formation enthalpy of methane we need to calculate. To get this net reaction, what I am doing, let us see. In the net reaction, carbon and hydrogen both are at left side, reactant side. CH4 in the right hand side. So likewise I am rearranging the above equation. So in the above three equations, carbon is there in the second equation. So I am writing the second equation as it is. And hydrogen is a third equation, it's the left side only. But how many moles of hydrogen is there in the net equation? 2 moles. But in the original equation only 1 mole. So for that what I am doing, I am multiplying the third equation with 2. Okay, so first second equation as it is I am writing. Why? Because carbon both are in the left side. That is why C plus O2 gives rise to CO2, whose del H2 value is equal to what? 393.5. Next, hydrogens left side in the third equation, but here 1 mole, here 2 moles we need. For that I am multiplying the whole equation with 2. So multiplying 2 into third equation. So write the equation. 2H2 plus 2 into half, it becomes O2, gives rise to 2H2O, and del H3 value, its value also doubles. 285.8 into 2, how it will be? 285 means 572.6. 571.6. Okay, clear. Next, in the product side, in the net equation, CH4 in the right hand side, product side. But in the first equation, CH4 in the left hand side. For that what I am doing, I am just reversing the first equation. See that in the forward reaction del H value was negative. If you reverse the reaction, the del H value becomes positive. Okay, so change the first equation, write the first equation in reverse way. That is what? CO2 plus H2O gives rise to CH4 plus 2O2, and del H value here negative, it becomes what? Positive, plus 890.4. Add these three. Okay, then see that 1H2O, CO2, sorry, here 2H2O will come. Okay, now 2H2O cancel. Next, CO2 will cancel, and then 2O2, here O2 plus O2, 2O2, here 2O2, all will be cancelled. So what is the remaining? That is what? C plus 2H2 gives rise to CH4. This is the original net reaction we want. So add these three values. If you add these three values, the net reaction del H value is equal to minus 74.7 something will come. Nearly 74 kilojoules. So but from the enthalpies of combustion, what we calculated? Enthalpies of formation. Okay, so this is the one of the application of enthalpies of combustion. So two applications. One is we can calculate the formation enthalpies of the compounds. The second one we can calculate what? Calorific value of the products. Enthalpy of solution. Enthalpy of solution we represent with the del H sol. Okay. So what is the solution? How you prepare the solution? Simply by dissolving the solute component in a particular solvent, we can prepare the solution. So when 1 mole of the solute dissolve in a particular solvent, okay, whatever the change in enthalpy, that change in enthalpy we call it as what? Enthalpy of solution. So the change in enthalpy when 1 mole of solute dissolve in a particular solvent is called enthalpy of solution. Even the enthalpy of solution is also exothermic or endothermic. It depends upon their hydration enthalpies and lattice enthalpy. Okay, so why? Because enthalpy of solution is equal to enthalpy of lattice energy plus enthalpy of hydration enthalpy. It depends upon these two enthalpies. Okay, so sometimes lattice enthalpy may dominates what? Hydration enthalpy. Sometimes hydration enthalpy may dominates lattice enthalpy. So in that case, del H solution can be a positive value or negative value. If it is a positive value, it's an endothermic. Negative value, exothermic. That is why I am telling enthalpy of solution can be exothermic or endothermic. Okay, next move on to the next enthalpy and most important enthalpy, that is what? Enthalpy of neutralization. Enthalpy of neutralization. We represent this with del H NEU or del H N also. What is neutralization reaction? Usually when we mix the acid to the base, if we get the salt along with the water, that reaction we call as what? Neutralization. So what is enthalpy of neutralization? That is when 1 gram equivalent of acid, 1 gram equivalent of acid reacts with a 1 gram equivalent of base, okay, getting the formation of H2O. Generally H plus OH gives rise to H2O. So when 1 gram equivalent of acid reacts with 1 gram equivalent of base, whatever the change in enthalpy, that change in enthalpy we call as what? Enthalpy of neutralization. This generally we represent with H plus OH minus gives rise to H2O. But remember that if the acid is a strong acid and a base is also strong base, when a strong base mixed with a strong base, a strong acid, when 1 gram equivalent of strong acid mixed with 1 gram equivalent of strong bases, always its del H value is always be exothermic. Remember that enthalpy of neutralization is exothermic and its value, del H value was 57.3 kilojoule per mole. Okay, enthalpy of neutralization of a strong acid and strong base is always fixed value, that is a 57.3 kilojoule, or else minus 13.2 kilocalories per mole. You remember this in 2 units. Sometimes they may give you the value in kilojoule, sometimes they may give you the value in kilocalories. In kilojoule 57.3, in kilocalories 13.2. It's a fixed value. Whatever may be the salt, acid base, you take any strong acid, HCl, HNO3, H2SO4, or strong bases, NaOH, KOH, cesium hydroxide, whatever it may be. Whenever a 1 gram equivalent of strong acid mixed with 1 gram equivalent of strong base, always the change in enthalpy was 13.2 kilocalories or 57.3 kilojoules. What is the reason? Why? Because strong acids to strong bases. When we call it a strong acid, whenever a substance is completely ionized in the water, complete 100% dissociation. Okay, here 100% dissociation, here 100% dissociation. So the net reaction is always be 100%. That is why its value is always be fixed. Suppose if you take either weak acid here or weak base, what will be? So in case of weak acid, weak base, that weak acids and weak base will not completely dissociate. There was no 100% dissociation. So in that case, here whatever the energy that was released, among that energy, some part of the energy it was consumed to dissociate. To dissociate some part of the energy it was consumed. So the net overall energy is going to be decreased here. So in case of presence of weak acid and weak base, enthalpy of neutralization is less than 57.3 or 13.2 kilocalories, because some part of the energy is going to utilize for ionization. Clear? So this is about enthalpy of neutralization. Next, move on. Here some examples I am taking. HCl plus NaOH gives rise to NaCl plus water. I am not writing the value, its value is always be fixed. And H2SO4 and 2KOH gives rise to K2SO4 plus 2H2O. Here the value is also fixed, you may get that out. Here H2SO4 and here 2 moles. Okay, so here 1 mole of H2SO4, its acidity was 2. Okay, and the 2 moles of KOH, so acidity was 1. Okay, but N factor values are same. That means 1 gram equivalent is mixed with 1 gram equivalent only. Don't be confused. Okay, if you are strong in mole concept, you can easily understand this. Okay, so this is about enthalpy of neutralization. Next, move on to the enthalpies of phase transitions. Enthalpy of phase transitions. So in this enthalpies of phase transitions, we will discuss 3. That is what enthalpy of fusion, and next one enthalpy of vaporization, and enthalpy of sublimation. Enthalpy of fusion, enthalpy of vaporization, and enthalpy of sublimation. Enthalpy of fusion, we write it as del HFUS. That not delta HF. Delta HF means formation enthalpy. Enthalpy of fusion is del HFUS. FUS stands for what? Fusion. And the enthalpy of vaporization, del HVAP or simply del HV. And sublimation is what? Del HSUB. So these are the symbols that we are going to use. Now, what is enthalpy of fusion? To understand this, you should know what is a fusion first. Fusion is nothing but melting. So, what is a fusion? The process of conversion of solids into liquids. You just take the ice. If ice melts into liquid, then that phenomenon is called what? Fusion. So, when 1 mole of solid is converting into liquid at its melting point, whatever the change in enthalpy, that change in enthalpy we call it as what? Enthalpy of fusion. Remember that all these enthalpies of phase transitions are endothermic, whose del H values are always be positive. You take any one of this. You take ice. Can you melt the ice into water without supplying the heat? Or can you vaporize the liquid into vapors without supplying the heat? Or can you sublime the sublimable substance without supplying the heat? No. So all phase transitions are endothermic. That is why all these 3, enthalpies of fusion, enthalpies of vaporization, and enthalpies of sublimation, all 3 are endothermic, whose del H value was positive. So how you define enthalpy of fusion? Enthalpy of fusion is nothing but change in enthalpy when 1 mole of the solid substance completely melts into liquids at its melting point. If you take the solid ice, 1 mole of the ice to melt into liquid water, it consumes what? Nearly 6 kilojoules of energy. 6 kilojoules of energy. So I can write H2O solid, H2O liquid. Tell me, here solid means ice, here H2O liquid water. They both are at equilibrium. This process we call as melting, and whose del H value is nearly 6 kilojoule per mole. Okay, next, enthalpy of vaporization. Vaporization means what? Conversion of liquids into vapors. So, okay, liquid water, if you heat the liquid water, it becomes what? Water vapor. And that process we call it as what? Vaporization. During the vaporization of 1 mole of the liquid water into vapors, whatever the change in enthalpy, that enthalpy we call it as what? Enthalpy of vaporization. So here, H2O liquid is converting into H2O gas, and whose del H value is equal to plus, I told you always be endothermic, its value was nearly 40 kilojoule per mole. So to vaporize 1 mole of the liquid water into vapors, how much of energy we need? 40 kilojoule per mole of energy we need. Next, sublimation. What is sublimation? You take a solid carbon dioxide. If you go to the functions, there they keep solid carbon dioxide. It will come out as like fog. Okay, it seems very beautiful. So solid carbon dioxide, if you take, also called dry ice. If you give the dry ice, directly the solid converting into vapors without the liquid, without intermediate liquids, directly the solids are converting into vapors, and that process we call it as what? Sublimation. So when 1 mole of the solid is directly converting into vapors, during this, whatever the change in enthalpy, that enthalpy is we call it as what? Enthalpy of sublimation. So here I am taking iodine. So if you take the iodine, violet in color, violet solids, so directly they are converting into iodine vapors, and whose del H value is nearly 62 kilojoule per mole. 62 kilojoule per mole. So these are the enthalpies of phase transitions. Next, enthalpies of transition. What is enthalpy of transition? You know, some of elements, for example, you take carbon. They can be exist in many allotropic forms. Diamond, graphite, fullerenes. Phosphorus, if you take white phosphorus, red phosphorus, and if you take the sulfur, rhombic sulfur, monoclinic sulfur, like this, many allotropic forms can be present for one element. And but remember that all elements doesn't show the allotropic behavior, only few of the elements, carbon, phosphorus, sulfur, etc. Okay, now transition means when 1 mole of the substance changing from one allotropic form into another allotropic form. Whatever the change in enthalpies during this process, that change in enthalpy we call it as what? Enthalpy of transition. For example, you take carbon. Carbon, most stable allotropic form is what? Carbon graphite form. I am converting this graphite form into diamond form. Diamond form. And whose value is nearly, del H value is nearly 13.8 kilojoule per mole. Is it positive or negative? Definitely it's a positive form. Why? Because it's already stable form. To convert this stable form into another unstable form, definitely it needs energy. That is why it's an endothermic process. Suppose if you take the reverse, diamond to graphite. Okay, generally diamonds are more strong compared to the graphite. So to remove that bond, initially they need energy, but after some time it releases more amount of energy. The net resultant value will be negative there. So whenever you compare the two products, one is exothermic product and an endothermic product, exothermic products always be stable compared to the endothermic products. So this is about the enthalpies of phase transitions and transitions. And last topic, that is what? Hess law of constant heat summation. Hess law of constant heat summation. As we know, the heat content of the system at a constant pressure we call del H, change in enthalpy. The heat content of the system at a constant volume we call it as change of internal energy. So heat content Q, heat generally we represent with Q, at a constant pressure, QP is nothing but what? Del H, enthalpy. It's another definition of enthalpy. Okay, the heat content of the system at a constant pressure is called enthalpy, and heat content of the system at a constant volume we call it as what? Internal energy. See, if you see both of these, both del H and del U, both are heat contents only. Both del H and del U, both are state functions, not path functions. What do you mean by the state functions? these values depends only on initial and final states, not on the path. Okay, that is the same here. Here both del H and del U, these are the state functions. How you would calculate? First, del H is equal to HF minus H initial, final enthalpy minus initial enthalpy. Del U is nothing but UF minus UI. Okay, they are depending only on initial and final states, not the path. So, based upon this concept, they introduce one law, that is what Hess's law. So, what is a Hess's law? According to Hess's law, whether a reaction takes place in a single step or multiple steps, then the total heat content of the reaction remains the same. Once again, whether a reaction takes place in a single step or in a multiple steps, the total heat content of the system remains the same. So according to the definition, see, I am taking A to D. A to D. It is a reaction takes place in a single step and whose enthalpy was del H. When the A is converting into D, the total heat content is del H. The same, what I am doing, first I am converting the A to B. So its value was del H1. Next B to C, and whose value was del H2. And C to D, whose value was del H3. So according to Hess's law, what I said, a reaction takes place in a single step or in multiple steps. Here how many steps are there? Step 1, step 2, step 3. So whether a reaction takes place in a single steps or multiple steps, the total heat content remains the same. So accordingly, so del H is equal to, the total heat content of the reaction is equal to sum of these all heat contents. That is what del H1 plus del H2 plus del H3. This is according to Hess's law. Whether a reaction takes place in a single steps or in a multiple steps, the total heat content of the system remains the same. So let us take an example for this. Let us wind up with by taking this an example. I am taking a reaction, that is what combustion of carbon, graphite. C plus O2 gives rise to CO2. Whose enthalpy? We know that. What is the combustion enthalpy of graphite? That is 393.5 kilojoule per mole. Okay, next, when C on partial oxidation plus half O2, it becomes CO, and CO on partial oxidation, CO is converting into CO2. So same. Okay, here C is directly converting into CO2 in a single step. But in the second process, first C is converting into CO, next CO is converting into CO2, 2 steps. So we know that conversion of CO into CO2, here del H value is minus 283.5 kilojoules. We know these two values, but determination of enthalpies of C to CO is difficult experimentally. So in that case, this value we can calculate by using Hess's law. According to Hess's law, what is that? The total heat content is del H is equal to del H1 plus del H2. You consider this is del H2. Here this is what? Del H1. So del H1 plus del H2. So del H value is how much? Minus 393.5. And del H1 value we need to calculate X. And the del H2 value was minus 283.5. Then X is equal to, you bring minus 283 to this side plus 283.5. So the total X value will be minus 110 kilojoule per mole. So for any intermediate reaction, the enthalpies of any intermediate reaction, if we don't know experimentally, that value we can calculate by using Hess's law. Okay, so not only this, we can also calculate the lattice energy by using Born-Haber cycle. Okay, so there was a lot of applications to this Hess's law that we discuss in the next video. Until then, take care. Bye bye.